Okay, here's the final take on this car mileage data. We're going to run through several models and check some assumptions and sort of change things and see which model we like the best. This is pretty much what we did in class. I wanted to record it one more time so you could see it a little bit at your own pace. Alright, so the first thing we want to do is turn this origin into dummy variables. So we have three different categories, so we're going to make two dummy variables, one called Japanese and one called European. And I'm going to use this if statement like we did in the other video. So if that guy, lock in I equals that guy, and lock in 1, then comma 1, comma otherwise 0. Copy that over there, double check, yep, looks like it's right. Highlight those both, double click, goes all the way down, so there's Japanese, there's European, so we're looking good. Highlight those, drag them over here, and whoops, the wrong button. Control Z, delete that, so that they're all next to each other. Alright, so we have miles per gallon is our Y, our dependent variable, and these are our X's. So let's go ahead and just do our first model. Go to data, data analysis, and we're going to do regression. Our Y is our miles per gallon, and our X's are all of these guys except for not the origin. So I hit Control Shift over, lift my Shift button up, so I still have the Control button pressed, and then press left. Whoops, nope, the other way around. Yeah, that's right. So here we go. Control Shift over, lift up the Control button. I'm still holding the Shift button, and then push left once. And so then it unselects this last one. Control Shift down. Okay. Label is good. We're going to call this Model 1. We're going to click on Residuals, make sure it's there, and say go. Alright. So here's our squared. Our F-test is significant. Our p-values are significant. I was going to show you something. I didn't do this in class. I thought you might be interested in. There's this thing called conditional formatting. Maybe you've ran into this before. Under the Home tab, click on conditional formatting. You can set up rules. We can say less than. If we say anything that's less than 0.05, highlight. Right, so it just highlights everything that's less than 0.05. So that's kind of cool. And then if that changes, it will just change that, right? So if I change this number 0.01, it automatically highlights it. Alright, so that's that. So we're going to first check some residuals. We're going to highlight the predicted and the residuals, highlight all that. Then insert, scatter plot, and there it is. So this is the cornucopia guy that we talked about. Low variance here, high variance here, and then kind of curvy. Alright. So we decided we could fix this by taking the log of the Y, the natural log of the of our miles per gallon. So let's do that. Insert, and we'll call this ln of miles per gallon. So equals ln miles per gallon of each of those. So I type it in once, and then double click, it goes all the way down. Alright, and then we're going to do this again. So let's see, data analysis, regression, miles per gallon this time, and then all of our other variables. And this one we'll call Model 2. Make sure residuals is still checked. Alright, how does this guy look? So here's our R squared. It's gone up quite a bit. So Model 1, R squared was 0.82. We're looking now at 0.88. So we're still significant here. Highlight this guy. Home, conditional formatting, less than 0.05, hit enter. So all but that one. So that's actually seems pretty interesting. Alright, so let's check the residuals again. Insert scatter plot. Okay, so this guy is all crunched up. So we can fix that by double clicking. First of all, it's a lot easier to double click if you make this thing a little bit bigger. I did that without saying I did. Double click on it, and then say I want it fixed at 2. So you could even do it even more. You could say fixed at like 2.2 or something. That's pretty good. Alright, so now we see here that this is much more spread, or much more evenly spread across the mean. Alright, looks pretty good. Looks like there might be a little bit more variance right about here. And it shifts down a little bit here. But overall, it doesn't look too bad. Right, that looks pretty good. So if we talked in class that we would just go ahead and say, yeah, that looks okay. We're going to leave it like just the way it is. For sake of parsimony, we're not going to try to do anything else on this guy. So that looks pretty good. So I wanted to show you, though, if we did want to do something, how would we do it? Well, let's first kind of copy the data, put it in another place. This is easier done when the miles per gallon, let's see, is on the right side of the other variable. So let's say I wanted to compare cylinders to miles per gallon. Right? So I highlight those two, say insert scatter plot. So this is kind of hard to see because cylinders, they're not a continuous variable. So it's kind of hard to tell whether that is linear, so that one's not really a great example. So technically we could actually assume that these cylinders could be discrete, right? We could say it looks like there's 3, 4, 5, 6, or 8. 1, 2, 3, 4, 5 different types. And we could turn that into categorical data by making these zeros and ones, 4 different variables for zeros and ones. So we could do that, or we could even say, if you're 3 and 4, you're together. If you're 4 and 5, you're together. And if you're 8, you're by yourself. So that would mean 3 categories. That might actually make a little bit more sense. And after looking at this, then we might consider doing that. So, but let's find another one. Let's move this one over. About engine displacement. That there. Highlight those two. Insert scatter plot. Okay. So this one looks kind of curvy, right, with a lot of variance here and a little bit of variance here. So this one does a pretty good job of looking kind of an exponential, like a negative exponential distribution, or something like that. So we could do this, right-click, say add trend line. First do the linear. And this is what I like to do when I'm doing this. Make this really pretty big. So that's our linear equation. So there's our r squared. Right click, do again add trend line. Let's do a polynomial with order 2. Whoops. You gotta make sure that the polynomial, the equation in r squared is on there. So that's that one. So r squared is increased pretty good. Okay, so just by including a squared value, we could increase the r squared a bit. Let's do one more. Add trend line. So we could do, we're going to look at these pictures and see what's going on. It kind of looks, it's like opposite of this. It kind of goes down that way. So I think if we did this, it might kind of not really work to our advantage. Let's see, so here it is. It has a much higher r squared, well 7.72. The problem here is that this is going to be a negative exponential, which means if I were to do this, it would actually reverse the way it would end up looking like a positive correlation. It would improve the model, but it would be hard to interpret, is what that means. It would look more linear, except for that now we would have to take the miles per gallon, would reverse the sign in order to interpret even what it meant, because it would make all these numbers into a negative number, is what it would do. So let's do one more. Add trend line. Which one have we done? Power. Okay. Whoops. Do that. I always forget. Whoops. Add trend line. Power. And then make sure you display the equations on the chart. So it's down here. So this actually has the best r squared of all. It has the same problem, is it's going to raise it to a negative number. A negative fraction, in fact. And so it will actually reverse the difference. So let me show you what that means. What it wants us to do then, the best fit would be to, see, what was it? Let's just grab this guy, x, move it all the way up to the top so you can see it. That didn't work, did it? X. There we go. So it's really saying create a variable called engine displacement. Engine displacement to the negative, what was it, negative 0.549. Negative 0.549. So how would we do this? Well, we would just say, here's engine displacement, raise it to the negative 0.549. Right? So if I do that, now I want to try something else. Let's see, insert this guy. X and move. Oh, whoops, I did it the wrong way. There we go. So now if I create a scatter plot with these two, so this is my transform variable, it's going to look very linear. Scatter. That looks much better, although look, it's the opposite direction, right? So before it was like this negative thing, and now it's a positive. That's because we raised it to some negative number, which means now it's much harder to interpret what that even means. It's raised to a negative number, we have a positive relationship, although the regular number is a negative relationship. So although we could do this, it would improve the model. It's sort of hard to interpret. So first, this again, for the sake of parsimony, it wouldn't really make a whole lot of sense to do this. But these are the steps that you would go through if you wanted to try to improve the model even further, or to transform the variables a little bit better, to see which of these different transformations might make things a little bit better. So that's basically how we would do. So if we wanted to raise something, let's see, so we'll do one more example. So if I wanted to use this, what was it, this e right here, so e to the negative 0.003 times x, it would look something like this. This is an exponent, exp, and then it would be negative 0.003 times our x, which in this case is engine displacement. Alright, so we do the same, we do this for all of them. So this is the exponential one. Let's plot this one more time just so you get a feel for what this looks like. Insert cut cells. There we go. Highlight those. Insert scatter plot. So again, it looks much better, much more linear, although it's the opposite direction. So the same as this guy. In fact, this might have, I don't know, it's different. So it's like way close to the same as raising it to the power. Right, but again, it's really hard to interpret what this means, and so it's for the sake of parsimony, we probably shouldn't do this. All right, so let's go back to Model 2. So we decided this is okay. So the next step is to make sure that these residuals are normally distributed. So go back up to the residuals, go into data analysis, and now we're going to go after the histogram. Our input range are just the residuals. Hit enter. Let's put this in, oops, a new sheet called histogram 1, and we want a chart output, and the label is there, so click on OK. Alright, so we can just sort of make this big. This looks pretty good, normally distributed. We can make this a little prettier if we wanted to, get rid of that. Double click on these guys, get rid of the gap, and let's see, we could just highlight that whole row and delete it, and then turn that into 2. So that looks pretty good. Pretty good distribution. So finally, we want to make sure that these are there's not too much collinearity going on here. All right. So how do we do that? We go to data analysis correlation. Highlight all this data. Control Shift down. Labels in the front or first row. Let's call this correlation 1. Click on OK. Alright, so we get something like this. So in class I showed you that if you copy this guy down, and then just copy the data, click on the first one right here, right click, say paste special, transpose, skip links. Does like that. So remember earlier I showed you this little conditional formatting thing. We can do the same thing with this, maybe easier, greater than, we can find some number like 0.75. I don't know, maybe 0.8. Looks like it's going to be about the same. So it just highlights anything that's 0.8, right? And of course the ones in the middle don't make a lot of sense, but here's the ones that are highly correlated with one another. Okay. So we want to find these variance inflation factors, these VIFs. So how we do that is we highlight, we start with something new right here. It's going to look just the same as this matrix, so it has to be the same size. highlight all of those, and equal m inverse is the function, m inverse. And then we highlight the entire array up here, so the entire correlation array. Hold the Control and Shift button down at the same time, and then hit Enter. Control, Shift, Enter. And you should get these little brackets. See these little brackets up here? Alright, so what we're interested in here is the diagonal numbers, remember? So these diagonals is what we're after. Let's bold those. And we say if anything's greater than 10, or if the average is, these numbers are slightly different than what we got in class, huh? I wonder what we're doing different today. Oh, I included miles per gallon. Whoops. Yeah, of course those two are correlated. It's just the log of one another. So, apart from that, this part on is exactly what we did in class. I think. Yeah, that looks right. Doesn't it? Looks pretty close. So this stuff, yeah, that's weird. We don't need that. So in fact, we could just do this. Let's delete these. It's gonna screw up that part. Yep. Let's see. Delete that first. Delete these two. And let's get practice again doing this m inverse function. So remember, we have to highlight. Whoops. All of that. Then type equals m inverse. And then highlight that. Control, Shift, Enter. Whoa, didn't like that either. Let's try it again. Not sure what we did wrong. Equals m inverse. The array is all of this, guys. Oh, I know why. We have to also delete these top two up here. It has to be a perfect square in order for this to work. Delete those top two. So really, I did this pretty bad. If this is confusing you, I really apologize. We'll do this one more time here, so it makes more sense. So we didn't want to include these miles per gallon, right? So we don't include those in the correlation coefficients because we don't mind. In fact, we want miles per gallon, and for this case, log of miles per gallon to be correlated with our independent variables. That's what we're after. We want to know that relationship. What we don't want is the independent variables to be correlated with one another, right? So I mistakenly included these two when we did. I shouldn't have done that. So that's why we're kind of screwing up. So in order to fix this, I just deleted the miles per gallons on the columns and the rows. So now it should work actually. M inverse function. So whoops. First we have to highlight all of this. Remember. And then while it's all highlighted, type m inverse, and then select the array. Control, Shift, Enter. Yay, it worked that time. Alright, and it is, I think these are the numbers we got in class. Okay, good. So we're still only interested in these three things. So engine displacement has the highest one. So we're going to go ahead and do this without engine displacement now and see if we can get a less multicollinearity. So here's engine displacement. We have to move it to the end. I wouldn't delete it. I would just move it. Right, so if I did what I grabbed it off, I hit E, and get the little crosshairs, and then drag it over here, and then highlight E again, right click, and say delete. All right, that way, you want to keep the data. You don't want to delete it. But if it's on the end there, it's easy to remember that it shouldn't be included in your analysis. All right, so we're going to do the same thing. Data analysis, correlation. This time without miles per gallon and without engine displacement. And we'll call this correlation 2. Alright, copy that. Copy this guy. Right click here. Paste special. Transpose. Skip blanks. Make sure those are both checked. Click OK. Then we get the whole matrix. Now we can select all that. Delete it and type equals m inverse. Oops, m inverse. Select the entire correlation coefficient, correlation matrix, and hold down Control and Shift, and then Enter. Alright, so now what we're talking about here are these guys. Alright, and we want to make sure that the average of those is less than 5, which is down here is 4.5. So we're good. So we can actually safely assume that we don't have severe multicollinearity. We can kind of go forward with the model if we don't include the engine displacement, right? Alright, so what we've done so far then is we've taken a log transformation of our y, and we've also gotten rid of the engine displacement. And now we'll see what the final model looks like. So here we go. We'll go back to regression. Regression, here's miles per gallon is our y, the log of miles per gallon. And our x is cylinders, horsepower, weight, accelerate, years, Japanese, European. Labels, we're going to put this in one called Model 3. Click on Residuals, so we keep that. Click on OK. Alright. So here's our R² value, 0.87, essentially 0.88. We have a low p-value for our significance f. Go to Home, Conditional Formatting, less than 0.05. Okay, good. So it looks like we have a horsepower and weight. Year, Japanese, and European. So let's make sure these make sense. So that's one thing we haven't been doing, with each of these models. It's good to sort of make sure that these are making sense, right? That they are intuitive. So now we're sort of in the final model. We should definitely make sure that's the case. So our cylinders is negative. So as cylinders goes up, miles per gallon goes down. That makes sense. As horsepower goes up, miles per gallon goes down. That makes sense. As weight goes up, miles per gallon goes down. Accelerate goes up, so the faster you are, the miles per gallon goes down. That makes sense, I guess. As year goes up, miles per gallon goes up, so the newer car has better miles per gallon. Okay. Japanese has better miles per gallon, and European cars has better miles per gallon. So those all make sense. Let's one more time look at these residuals. Insert, scatter plot. Yeah, we always have to fix this a little bit. Double click in here. Whoops. Come on. There we go. And make us fix to a 2. Yeah, that looks pretty good. Doesn't look too bad. So we can again assume that that looks pretty good. Now, how do we interpret this? So actually, I think I did this in one of the classes and didn't really point out exactly how to interpret this, but let's say what one of these numbers means. So for example, year. So is for every year newer the car is, and we can expect a 0.03, essentially 0.029, 0.03 increase in log miles per gallon. Not just miles per gallon, but in log miles per gallon. Okay, log miles per gallon. So if we use this for a prediction, we'd actually predict log miles per gallon, right? So let's make an example of what I mean by this. So control copy, put this down here. So in fact, we could actually do it with these ones. Right, so we could say, look, here's our predicted miles per gallon. Well, these are all in logs, right? So in order to turn those back into regular miles per gallons, we just say take the exponent of it, and then that would be in terms of miles per gallon, right? So this is predicted miles per gallon. Right, where this is predicted log miles per gallon. So predicted miles per gallon, that's the difference between these two. Because that was our whole formula, our y hat here is a log miles per gallon. So if we want it back into miles per gallon, we have to take the transformation of that again, transform it back into that. So that means that if we interpret these, we have to interpret these in terms of logs miles per gallon. Although the relationship is still meaningful, right? It still helps us understand, which of these is kind of bigger and which one of these influences more based off of these coefficients. All right, so that's that. Let me know if you have any questions, and we'll see you in class.